Today we are going to talk about machines. We've been discussing the 6 types of simple machines, so today we're going to talk about why we use a machine, what's the purpose, and how efficient are they. So what do we think of when we hear the word machine? Take a moment to fill in that question on your sheet. And then also answer the second one. Why do we use machines? So today we're going to try to answer these 2 questions as we go along in our notes. So what is a machine? So a machine is just a device that makes doing work easier. So it either changes the direction in which we apply a force, we have to apply less force because we're using the machine, so it makes our work easier. So machines can be as simple as a knife, a scissor, a doorknob, a lot of everyday objects. They make our work easier. So even though they make the work easier, we still have to do the same amount of force. So if it requires 10 joules of work in order to move a box up into a truck, we still have to do that 10 joules of work, no matter if we're using a ramp or if we're simply lifting it upwards. Okay, so we still have to do the same amount of work, but it makes the work easier. So there are 3 ways in which a machine can make work easier. So 1, it can increase your force. So you apply a 10 Newton force and the machine applies a 50 Newton force to the object. So it increases the force we apply. It could also increase the distance. So here is the good example of a ramp. So instead of lifting a box straight up, which can be a lot more force having to be applied, we push it up a ramp, which requires less force, but we have to push it for a longer distance. And then the third way a machine can make work easier is by changing the direction. So this is an example of like an axe. So you apply a force downward, which is easier to swing down for us, but it pushes outwards on the log to split it. Okay, so it makes the work easier, but we still have to do the same amount of work. So another example of increasing our force would be a car jack. So a car jack increases the force we apply. So we push down with a small force, but the jack pushes upwards with a greater force. So it multiplies the force we apply. Okay, another one for increasing distance is a ramp. So the work stays the same, but we increase the distance. So pushing up a ramp, we require less force, but we have to push it for a longer time period. And then our axe is their example of changing the direction. So when you use an axe to split a wood, you exert a downwards force, which is easier to swing downwards, but the blade changes that force and pushes horizontally outwards on the wood to cause it to split. So we can calculate the advantage of using a machine. We call that the mechanical advantage. So the higher our mechanical advantage is, the more advantages, the better that machine is at doing the work for us. So we calculate our mechanical advantage. It's just a ratio. So we take our output force divided by the input force. So the input force is the force that we apply. And the output force is the force that the machine applies on whatever object you're trying to do work on. So the bigger this number is, the greater than 1 it is, the more advantages to using that machine. If it's less than 1, that means that you're doing more work or more force on the object than the machine actually is. So that would be a bad machine to use. So the bigger the number, the better the machine is at doing the work for us. So let's practice calculating one. So we want to calculate the mechanical advantage of a hammer if the input force is 120 newtons and the output force is 2,000 newtons. So MA, mechanical advantage, it doesn't have a unit, it's just a ratio. So it's the force out divided by the force in. Okay, so it says their input force is 125, so that goes on bottom. And our output force is 2,000. So we're going to take 2,000 divided by 125, and we get a mechanical advantage of 16. So again, it's bigger than 1, so it's more advantageous to us to use that machine. And we could compare it to other machines that would do the same work. The bigger the number, the more advantage we have using that machine. Okay. We can also talk about how much work is put in and how much work comes out. So ideal machine, so the perfect machine where there is no friction present, the amount of work we put in should equal the amount of work we put out. So none of that work is getting lost to friction. So we do things like greasing up engines, adding oil to reduce that amount of friction. But nothing is ideal in the real world. And so a non-ideal machine always has less work that comes out because we lose some of that work to friction. So we can calculate the efficiency of how much work we put in and how much work we get out is a measure of that efficiency. So a machine with a high number, so a high percent efficiency, means it produces less heat because from friction, so not a lot of friction. So more of the work that we put in is converted into useful work out. So if you've ever noticed a car after you've driven it for a while, you touch the engine and it is hot. So it loses a lot of all that work we're putting in by burning that fuel. It loses a lot of it to friction and heat. Cars are only about 25% efficient. So 25% of all the work the car does gets turned into motion. So that means 75% of the work in a car gets turned into friction and heat. Now, some of the newer cars can get like 30-40% efficient, but still more work is getting converted into heat and friction in cars than it is to actually causing the car to move. So they're not very efficient machines. Okay, but we can calculate the efficiency of any machine by using this equation. So our efficiency is equal to the work out divided by the work we put in times 100. So times it by 100 at the end will give us a percentage. So the closer we are to 100%, the more efficient our vehicle or our machine is. So let's calculate this one. So find the efficiency of a machine that does 800 joules of work if the input work is 2,400 joules. So our efficiency equals the work out divided by the work in, and then we're going to times it by 100 to get it to a percent. So output work is our 800 joules, and it says our input work is 2,400, and we're going to times that by 1,000 to get it to a percent. So remember, the closer we are to 100%, the more efficient our machine is. So 800 divided by 2,400 times by 1,000, or so times by 100, and we get 33%. So this machine is not very efficient. Remember, the closer we are to 100, the more efficient it is.